All right, so welcome to something new. Okay, this is lecture 16 on searching. And what we're going to do is we're going to start by doing something incredibly strange because our data structures are becoming more and more complicated. For example, as just asked, now we've got like this list of dictionaries. Okay, and by the way, yeah, you need these things. These are going to become really important for the lab exam because guess what? There's probably going to be a list of dictionaries. Just like on the assignment that you have a dictionary filled with dictionaries. Okay, I don't think any one of these combinations is more difficult than the others, but it is something you have to keep in mind that if you have lists inside dictionaries inside lists and so on, you have to be able to deal with each of these things. Now, just as a quick, let's call it a community service reminder, in terms of dealing with the lab exam, okay, you notice that I did post something a little while ago to say that, yes, this is what's coming on the lab exam, so we'll look at this one first. Basically, it's everything up until like, okay, it's not specifically now, but searching using a linear search, by the way, is something we've always done, so yeah, that's still fair game. Basically, it's everything. It's lists, sets, tuples, dictionaries. So yeah, it's a bit different than last semester because we've pushed the lab exam back a couple of weeks, so there's more than ample time to cover dictionaries, and I think it's important because they're actually the most important thing of this entire course. And we also include nested structures, which is things like lists of sets, lists of dictionaries, and whatever combinations you want. And just as a catch-all, I said everything from the start of the semester, including INFS 1101. Okay, the reason why I put that, no, I'm not going to ask you to write a flow chart, but I have to include this because somebody says, oh, you didn't say I was going to include while loops. Okay, basically it's everything. Okay, so that's why I've put it here. Okay, so no, there's not anything that we're not going to cover. The only thing is I'm not going to ask things about binary searches, which we'll see today. We won't see things about sorting, I can guarantee that. But basically up until like, well, basically the first part of this lecture, I guess, would be part of it because we will be doing with searching. Now, in terms of questions, we have been using 5 coding questions. That will be the same setup. 3 of them, where 70% of the lab exam grade, are considered to be relatively straightforward. Okay, I have to be careful about the word relative. That doesn't mean that they're simple. It means that there's things that I expect that you would be able to do if you understand what's going on and can write programs. You'll have no issues with the first 70%. The last 2 questions will be more challenging, kind of like what we did on the midterm. It's worth 30%. In other words, the idea is that it should be possible to pass if you know what's going on, but you shouldn't get tripped up on these really tricky questions because the tricky ones, they will show up at the end. They're worth smaller points. So just look at the point value. Well, actually, just look at the order. The first 3 should be relatively straightforward. The last 2, a little bit more of a challenge. In terms of the easier questions, yeah, it will be based on the correct results, and there will be a small number of points available for dealing with the algorithm and logic and so on. But generally, it's if you have a program that doesn't run because it's full of syntax errors, sorry, that's actually not acceptable. We really don't give any marks for it, or we really shouldn't give very many marks for it, because you have access to an interpreter, and if it says that, hey, you've got a variable that you're trying to use the value but you never assigned it, well, okay, that one is something that we expect that you'll be able to deal with. Okay, and the same as on the midterm, the last couple of questions, mostly it's either it works or it doesn't. The only option is sometimes if it works in the general case but you missed an edge case, you might get most of the marks. In order to prepare you for the lab exam, I have provided a whole bunch of information. First of all, I've provided a copy of every lab exam problem that we've had since I went back as far as fall 2023. If you've noticed in this list that like fall 2023 looks like it had 1 question, that wasn't the case. There was actually more than 1 question, but the other questions didn't make any sense for a lab exam. I would not want to give you an easy question and you say, oh, it's going to be just write a function to check a string. No, that's definitely not what's going to happen. Yes, you will be given functions. You will be given one of these data structures. Maybe you have to find something. Maybe you have to build a new data structure. Okay, these types of things. So I went through all of these. I basically copied absolutely everything. So there's a big pile of questions in here. So yeah, work your way through them. I'm not providing solutions to them. You need to work through the solutions on your own. Okay, if you get stuck on something and want some help, by all means come and see me, see your lab instructor and say, hey, I'm getting stuck on this, what should I do in order to work through this? Okay, so please work through these things. The only thing that's missing is there are no questions about dictionaries. Okay, because we haven't done this before. But in order to deal with that, I have given you this little brown or orange colored prompt. You can copy and paste that into ChatGPT, and it should give you some questions that are kind of appropriate level. Okay, that's why it's a big long description. It isn't just give me some Python programming questions, because it will give you all kinds of crazy things. But this should be pretty close to the types of things that I would expect. In fact, this is pretty similar to a prompt that I might use sometimes to produce ideas for programs. Does that mean I'm using ChatGPT? Sometimes to give me an idea, but I always have to change it because you know how this works. It's not always exactly what you want. But I think most of the things, when I generate it this way, I look at it and I go, yeah, that's fair game. They're pretty reasonable. The only thing that I don't like about ChatGPT is it's not very inventive. In other words, it always gives you the same stuff over and over again. It's libraries and books, it's students and grades, it's inventory items. But you know what? If you do enough of these, you should be able to apply this to any other issue, any type of other problem domain. All right, the final thing that I've included, you will find that there's an area here called practice questions. This was a set of lab test practice questions we gave a couple of years ago. They're a little easy, I think. They're not the greatest, but hey, it's some extra questions I don't mind you working on. And there's also a section here called programming dictionaries. Again, it was some questions that we gave in practice for the final exam when we didn't cover dictionaries till then. Okay, so there's a lot of stuff in here. Okay, so if I do all of the exercises and I do all of those things and I generate 100 questions out of the ChatGPT and I do all the lab exercises and I can solve everything without an issue, will I do fine in the lab exam? I could probably say yes. What if I know all the answers to the labs? No, okay, it's not enough. You don't need to know the answers, you need to solve them. Okay, and that's always my danger when somebody says, is this enough? The answer is it enough? Depends on how much effort you put into it. That's really my biggest warning about this. All right, let's get this out of the way and let's actually begin the lecture for the day. Okay, and we will even take a full week, not next week, but I think the week after. In the lecture, we'll take a few problems and we'll solve them. I don't know which problems we'll pick yet, but we'll figure that out. Okay, so there will be a review as well. All right, searching. Okay. Searching refers to trying to find something. Okay, and yeah, I'm going to be flipping back and forth between the slides and the interpreter here to do a couple of quick demos of things a bunch of times today. So the word searching is something that does appear in programming, and it means you've got some value that's hidden in a collection, usually a list, and we're going to make it really simple today. It's just going to be lists, although what I'm applying here, well, some things will work for a list and some things won't. I'll try to remind myself to ask this question about what do you think, whether or not it applies. All right, searching means you've got a list of items and you want to know whether or not something is there. That's the whole purpose behind searching. All right, the book that we use from OpenStax has absolutely nothing in it, so sorry, you'll have to refer to the appendices. I wrote up a bunch of stuff for linear searches, binary searches, and searching complex objects. So basic searching. Okay. Let's write some code because that'll be more interesting than just looking at slides. Definitely more interesting than reading whatever slides are here. Let's have, okay, I hate always searching for test scores. All right, here we go. Students, okay, it's a list of students. 6006, 1, 2, 3, 4. Yeah, what I'm gonna do is I'm gonna list off a bunch of students, or at least things that look like a student ID. Okay, and 6010, and maybe another one, 6070. Hey, we're into the future. Eventually we will get there. 6009. That's too many. Okay, I just want to keep them more or less the same. All right, and maybe 60103321 and 60111110. Okay, there we go. There's a bunch of students. You just give me a second because MySQL Workbench is driving me insane. All right, excellent. Sorry, what's the question? Yeah, it's not closed. Okay, excellent. Okay, that wasn't a test for you. I just hadn't gotten there, but oh, it was the wrong one. Okay, that was a test. I'm sure it was. All right, here we go. So we got a bunch of students, and I suppose I should have made the numbers easier. All right, so bear with me as I read the numbers. Is the ID, is the student 600123343 in my list? Yes. Yeah, good. Okay, so there's one question I might want to ask is there something there? Okay. Another question that I might ask is, where is it? What's the position?
Position 2.
Yeah, position 2. Okay, very good answer. All right, now we'll make this one easy. Is the student 7000000 in that list?
No.
No, it isn't. And what's its position?
None.
Yeah, it's none. Okay, that's kind of a good answer. Now, there was kind of a trick that we used to do. I'm going to call it back in the old days. I wouldn't do it in Python but we certainly could. Sometimes if we were searching for something and you say, tell me the location of the ID 7, which isn't there, sometimes we would end up returning back the value -1 to say it wasn't there because -1 wasn't actually a valid location. It's just some kind of it's just an idea to say it's not there. Yeah. Okay, so all of these things, by the way, might jump out at you if you go into a different programming language. And one thing that I always have to remind students is the reason why a lot of the things that we cover, like especially today, is kind of a little less applicable in Python. But remember, the course, although you guys call it Python 2, sometimes, the official name of the course is computer programming, so it should be stuff that's applicable to all the languages. So yeah, even though we've got some shortcuts in Python, we try to talk about other things in general. All right, well, here's what I want to do is I want to write a function to tell me whether or not the student is there. Okay, so pretty simple. I want to know the question, well, let's just call it find student. Student. Now, there's a couple of things that I would need to pass in if I'm trying to find the student. First of all, I would need a student list. And the second thing I would need is, who am I looking for? Okay, so I'm just going to call it find for right now. And you know what I'm going to do. I'm going to return none. I'm just going to set this up. I'm just going to say print find student. I'm going to pass in my student, and I'm going to search for something like 600123343. If I make it 5, it'll be easier to say. Okay, and I'll have less trouble. All right, here we go. So we run this, obviously it just returns none. I just want to make sure everything's in place. Now, let's try to detail what it means to find a student. Okay, well, to find a student, when you have a list of students, well, I mean, we've done this a whole pile of times. That's why the searching that I'm talking about right now is not something new, and it certainly isn't scope on the lab exam. How do you find something in a list of things? Well, we've done it a whole pile of times. Yeah, you iterate through the items, okay? And you have a couple of options here. Okay, so let's first of all start with, let's return true or false whether or not the person is there. Okay, that'll be my first one. Okay, exactly as you suggested. I will go for S in student list, and of course, well, yeah, that's S happens to be this, and you know what, just print it, okay? Yeah, there's everything. I'm not interested in all of these. I'm probably only interested if S happens to be equal to the thing called find. Okay, let's run this one. Yeah, it's there. Okay, so it prints in this one. And if I ask for something that isn't there, like 1, 2, 3, 4, 7, it doesn't print it. Okay, we're part way there. Let's put it back. You see, if I find what I'm looking for, well, we just decided a few seconds ago we would like to return true. Okay, so there you go, done. Oh, okay. So you see, if I run this, it says true, and if I ask for something that isn't here, it returns none. Okay, okay. I don't like true versus none. I'd rather have true versus false. Okay, so that's pretty simple. Instead of returning none, it's return false. There you go. So now it's either true or false. It's either there or it's not. At this point, I could now put it into an if statement and say, if find student is equal to true, then I could say that yes, the student is here. Otherwise, I can say no, the student is not, the student wasn't found. I have to warn you about something because this always ends up happening, okay? And I believe that I've already said it before, but the number of times that this mistake is made, especially in an intro programming course, is actually quite staggering. In fact, it's also very disturbing when I see it in a third-year course as well. That means that the students have made it through without quite understanding something. And my question is this going to work? All right, well, first of all, let me go back and ask for 600, 2, 3, 4, 5, and I'm going to ask you, what should the function return at this point? This should be true because it's definitely there. Unfortunately, if we execute this, it says no, it isn't. And the reason why it isn't found is, well, work through the tracing about what happens. Remember, that's why I said you have to understand the tracing, those MCQ tracing problems, because you have to understand why is this not working. All right, remember, we go through S in all the values. Hey, S is debugging. If you ever get stuck, print it. Take a look at this. You see, the only thing that we saw was 6006, 1, 2, 3, 4. We didn't see anything else. Why? Well, trace it. You see, when I printed 6006, 1, 2, 3, 4, the next thing I ask is S equal to what I'm looking for? And the answer was no, so therefore, return false.
Okay.
Return means end of function. You don't do anything else.
Yeah.
Okay? Yeah, you need to iterate through to the end. And if you don't find anything when you finally reach the end, okay, at this point, now you can finally conclude that they're not there.
Yeah.
Okay? You can't just look at the first person and say, yeah, that's not the student I'm looking for, so therefore they're not around. That just means that they weren't the first student. Okay. Now, I got one small modification. Okay, so this comes out of here. Okay, and we'll put this back, and congratulations, we basically have ourselves a what's called a linear search. We'll talk about that in a few seconds. Usually when we're searching for something, we call it the key. Okay, it's just going to be a name we're going to use. So the key is the thing that we're searching for. Obviously at this point, I'm going to get rid of this one. Okay, so simple enough. This is one way. What if I wanted the position instead of knowing just whether or not it was there or wasn't there? Okay, well, the usual approach for dealing with where is the location, you would instead have to go back to using an index. And you've seen me do this a pile of times for this in range length of student list. All right, so first of all, let me just print index so I can remind you what we get. Okay, those are the indexes, position 0, position 1, position 2, and so on, all the way up to position 7. I'm not interested in all of these. I want to know if the student list at the index happens to be equal to the key. If it is, then I'm going to return, now, obviously I could return true. Okay, and I'm back to the same problem. It's just a different way. But if I instead return index, you see, now what I'm starting to get back is I'm starting to get back to location. Now, to be a little bit more consistent about this, is that student there? And the answer is no, and right now it returns false. Again, I don't like this as a function design because sometimes it returns an integer, sometimes it returns a Boolean. When you go into a much more strict programming language, such as Java, for those who will continue on the IT program, all the return types have to be the same type. And as I was saying earlier, a trick that we used to use, I'm going to say a long time ago, is you would do something like this. So if you don't find something, you return a -1. A -1 is a special indication to say that, hey, don't look here. Unfortunately, -1 in Python means the end of the list. So it doesn't quite work. And to be honest, in Python, most people would probably return, not negative none, but they'd probably return none. I don't like it, but it would be acceptable. Okay, and then the rest of your program can make the decision. Okay, now let me put, again, why is MySQL Workbench looking for my attention? Please disconnect. Okay, let's get over to here and say there are two basic common goals for searching. You either want to know whether or not the element exists in the list, and the second one is, where is it? Okay, so the simplest method is something called a linear search. What you do is you start at the beginning of the list and you check each item, and if you find the match, yeah, you're finished. Oh, we just implemented this. Okay, let's go through and take a look at a couple of graphical examples. So no code this time. All right, so the first one up is we've got a list of, I don't know, maybe they're test scores or something, and we want to find out the location of 75 or whether or not 75 exists. So using the second one where I was using the index, you see what I was doing is I said, okay, I basically asked the question, is that the 75? Is that what I'm searching for? And the answer is no. So what do? You add 1 to the index. Okay, is that a 75? No. Is that a 75? No. Is that a 75? No. Is that no? Is that no? Is that no? Is that no? Okay, here we go. Is that a 75? No. Is that a 75? Yes, so therefore I can stop and I don't have to look any further. Okay, all right, fine. What if we search for 45? Okay, so same operations. So we ask, is that a 45? No. 45? No. 45? No. 45? No. 45? No. 45? No. I think you get the idea, right? You see, what I'm going to do is I'm going to continue going, and how far do I have to go? Right to the very end. And finally, when I reach here, I go, is that a 45? No. Well, now I've reached the end, so therefore, it wasn't there. And at this point, I can return false, it wasn't there. I can return a -1 to say it's, or none to say that it's not in the list. But here's a bit of an interesting problem. You see, in the worst case, which happens to be when the item isn't there, you end up having to look at absolutely everything. Now, this is a topic that we talk about in a third-year course called Data Structures and Algorithm Analysis. So we don't do the algorithm analysis here, but we still talk about this at the same way. With this approach, this particular algorithm that I just gave you, in the worst case, you have to look at everything. So in other words, if you had 10 million elements in your list, then you have to search through 10 million things to find out that something wasn't there.
Yeah.
And that can be really, really, really slow. And you might say, okay, well, who cares? All right, I always put this into a context when I'm teaching the data structures course is, okay, put it into something of a mind of a student. All right, hey, we used to do the same thing, except our games were really rotten. Everybody likes to play games, okay, like 3D type games where you're going off and shooting people. When you fire a bullet, how does the program know what you hit? Well, it will go through each of the items possibly in the room, and it'll find out whether or not the bullet crossed paths with that location. It's obviously a little bit more complex than just looking to see if it's equal to 45, but it's the same idea. And if you have a million items in your room, guess what? You're going to have to go through a million items to find out that, yeah, you missed everything. The more time you spend searching, it means that you're going to get a lower frame rate. Nobody wants lower frame rates. You want like super fast frame rates. Okay, so maybe this is not the best solution. All right. Okay, warning, danger about what I'm about to describe. In fact, I'm thinking I'm looking at it and I might remove a couple of things. What we just described actually falls into a category called a linear search. Okay, that's in scope. This is called a linear search. Yes, you need to know that. In the worst case, you have to look at every element. Good. You have to know that. We understand that. The next bullet point is not so critical for here. It's kind of more of a third year thing, so sorry, probably reusing some slides. But the idea is that if you have n things in your list, then it's going to take a function that looks like this. It's c times n plus c2, which is small constants. But basically what this means is if n is a really big number, it's going to take a long time. If you double the size, it's going to take double the time. Okay? That's actually the reason why it's called a linear function, is because the time required is a linear function. So you think back to your math course, you learn what a function is, like f of x. Well, if f of x is equal to ax plus b, that's a linear function. That's exactly what I've got here. It's a straight line. Okay, you double the size of the input, doubles the amount of time. That's all we need to worry about. Don't worry about the function, don't worry about the equation. You're never going to see it again after this slide. Okay, but what I do want to say is that it's not a good option if you need to search the large list frequently. And we'll see an example, hopefully I don't run out of time, at the end where this is going to bump into. Now, because we're here, did we really need the function to find out whether or not this student was inside? Oh, well, actually, you see, Python comes with a bunch of stuff built in. There you go. Yeah, that's not in the list. Oh, I just need to do that. I don't need to write the function? Yeah, of course. And if I ask for 1, 2, 3, 4, 5, is that in the list? Yeah, it is. Oh, so single line. But guess what? It's still a linear operation. It still works exactly the same way that I described. It just happens to be built in. Oh, perfect. So we don't need to know that. Yeah, you don't need to know that till you try using it for real operation. Okay, and I will explain that one a little bit later. The second one, which is very, very useful, is there is another operation called index 600, 2, 3, 4, 5. What this does is it returns the index of what you're searching for. That's the other one. How do you think it works? Exactly the way I described. It goes to the first element, checks and checks and checks and checks and checks until it finds a match, and then it returns it.
So we should just use these functions.
Oh, if you can, sure. The only thing that's kind of nasty is if 600, 1, 2, 3, 4, 8 is not in the list, it will crash instead of just returning like, yeah, I couldn't find it. Okay, but yeah, this is the way how Python programmers would think. You wouldn't write a linear search on your own. Oh, good. So why am I covering it? Because we're going to see a real life problem in a little bit, and it's not going to work. Okay, it works perfectly fine for this because this is kind of an unrealistic problem. So we have to expand things to make it a little bit more realistic. But I've got another algorithm first that I want to talk about, and then we can talk about the implementation and using it for real life. So if the data happens to be sorted from smallest to largest, actually it works the other way too, but for the purpose of today's lecture, you can use this really cool and clever technique called a binary search. Again, it's something that we really cover a lot in third year, but I think it's important that even a first year programming student really needs to know that these things exist. Okay? They're not difficult to implement if you take it the right way, and it can really speed up a lot of programs. In fact, I hope we have enough time to actually try speeding up a program before we finish. And sorry, I think the day is probably going to burn almost a full time. Sometimes it happens. All right, here's the way how it works. Basically, you look at the middle element, and you make a decision about if that's what you're searching for, you're finished. Otherwise, you throw out half the array. Now, although the words are listed here, it's actually much easier to see in the form of a picture. Okay, so consider the following list. Now, of course, this list has something very, very important about it, and that is, take a look at the values. What's suspicious about the values that are here? Yeah, they're sorted. It's going from smallest to biggest. I know that there's also no duplicates. It's not a requirement of the algorithm, but usually when I demonstrate it, I remove the duplicates. It still works, even if there are duplicates, but it's just like one extra thing I have to think about. All right, so here's what we're going to do with this sorted list, which is really, really important. And this algorithm, by the way, doesn't work on list things that are sorted. Let's go back and search for 75. So, I mean, I guess the first question is, where is it? Or is it there? So I guess the first question, is it there? Yeah. Where is it? Position 10. Okay, how'd you find it? You went across probably pretty quickly from the beginning to the end, but you may have also been able to skip quite a bit because take a look at this. I mean, if you look around here and you see numbers like 9 and 18, guess what? It's not going to be here. It has to be between numbers that are it has to be higher than numbers that are less than it, and it has to be bigger than numbers that are, before numbers that are bigger than it. All right, so here's what I do. I pick exactly the middle of the list. Okay, so which exactly is the middle of the list? You just saw it a second ago. Okay, how did I know that's the middle of the list? Okay, I used a very simple, straightforward calculation. Take a look at all of the white cells, okay, because this is going to be really important. The color is kind of important. We'll see how this gets implemented. What's the location of the first white cell do you see? 0. Okay, what's the location, or what's the index of the biggest, the last one? 16. Okay, what you do is you take 0 plus 16, and that gives you 16. You take 16, you divide it by 2, and it gives you 8. That's the middle. Okay, so what I do is I look at exactly the location in the middle and I say, is that what I'm searching for? And the answer is no, it isn't. But everything less than 8, is there a chance that it's going to be over there? And the answer is no way, because it's sorted. So in other words, what I can do is I can now throw out half of the array. Okay, so what I'm going to do is I'm going to mark it with a, I didn't have any choice over the color, it kind of came on its own. So apparently it gets marked with dark blue. Okay, and we know that there's no chance that 75 is going to be, I don't have to look at it because I just looked at one value and I said 69. Look, 69 is less than 75, so therefore everything, including the position number 8 just gets tossed out because it's irrelevant.
Yeah.
There's no way that it can be there. If it is there, it means you don't have a sorted list, and this whole algorithm is out the door. Things had to be sorted for it to work. All right, we repeat again. Okay, so I've got a bunch of elements. We only look at the white ones, okay, the ones that I haven't actually processed yet. And we need to find the middle. Okay, same process. What's the smallest value? Or sorry, what's the position of the first white cell? 9. Okay, and with the other end? 16. Okay, 9 plus 16? 25. 25 divided by 2? 12.5. Okay, but can you go and look inside list position 12.5? No. So what we do is we'll just truncate. I mean, I guess you could round it. Most of the time we just throw it out. Remember, / does exactly what we're looking for, floor division. That's what it's here for. So I go directly to this location. I say, is this what I'm looking for? And the answer is no, that's not what I'm looking for. But I found an 85, which is bigger than what I'm searching for. So therefore, I know that 75 is definitely not in 12 or anything to the right. So I'm going to get rid of everything else. Now I'm down to 3 spots. All right, so the smallest position, that's currently white? 9, okay. The highest? Okay, 9 plus 11 is 20. 20 divided by 2 is 10. All right, so let's look there. Is that what I'm searching for? Yeah, good. Okay, excellent. I'm finished. Okay. Now, that's really cool because if it had been a linear search, I would have had to search through 11 things to find it. Yeah. And now I only had to actually look at 3 values. Let's repeat it again for the 45 because 45 is interesting because it's not there. So this has got to be the worst possible case. All right, so we start again. Same location, in the middle, 8. Okay, and I say, okay, 45, no, I found a 69, so basically I'm going to ignore everything on the right-hand side. Okay, right-hand side's this way, and I'm going to repeat it. Oops. Yeah, now you got it. Okay, 0 plus 7 is 7. 7 divided by 2 is 3.5, but of course truncation. Yeah, we look at this and we ask, is this what I'm searching for? No, unfortunately not. But because it's a small number compared to what I'm searching for, I'm going to toss out the entire first part. All right, and we repeat it again. Okay, what's between 4 and 7? Okay, 4 plus 7 is 11. 11 divided by 2 is 5.5, truncated down to 5. So I repeat again, is this what I'm searching for? No, but I know something about it. What I'm searching for is bigger. Therefore, I can toss out everything that's on the left-hand side. Okay, and I once again ask, okay, what's in the middle between 6 and 7? Okay, 6 plus 7 is 13. 13 divided by 2 is 6 after you get rid of the 0.5. And I ask, okay, is that what I'm searching for? And still no. But this is less than what I'm searching for, so therefore I toss out this and everything to the left. Okay, now I've got one element left, which is at position 7, and you take 7 plus 7, which is 14. 14 divided by 2 is 7. So there we figured out the thing in the middle, and I asked, is this what I'm searching for? No, it isn't. But what I'm searching for is less, so I throw out everything that appears to the right-hand side, and of course now I've got nothing left. So now this means that obviously it wasn't there. Okay. How many times did I have to look? I looked at 5 elements. Compared to a 17 from before. Oh, and if you're wondering whether or not this is sort of extendable and we can continue to make this problem more and more interesting, like what happens if we have like 1 million elements? Okay, the linear search, when you don't find something, you have to go and have to look at 1 million things. Want to take a guess how many things you'd have to look at using this algorithm for 1 million? We don't cover it in this course, but take a guess. No, it's a bit more than 10, but it's not much more than 10. It's actually double, it's 20. 20 is a big number, is a big difference compared to, say, 1 million. Okay, and if you go up to, say, 4 billion, I mean, that's a lot of stuff. 32 is the magic number. 32 steps, and you'd find whether or not something is there or it's not there. It's a very, very powerful algorithm. Yeah.
What happens if you search for something like this, but They're still the same number.
Okay, that's why I left out the duplicates. It's a little bit trickier. It will work and it will tell you whether or not something is there. Okay, the algorithm still works. You just keep applying the same process, except instead of saying if it's just strictly less than or greater than, you have to say if it's less than or equal to or greater than. You make your decisions. It gets a little bit funny if you want to find out like all the locations. It's kind of tricky, but to know if something is there, it still works. Okay, you can give that a shot. Okay, so let's try implementing it. I promise it's actually not that difficult. All right, so here's what I'm going to do. Let's have some values. Okay, 2, 3, 4, 9, 18. I should have put these in place already. 39, 40, 55, 69, 71, 75. Okay, it doesn't really even matter what I've got, but it does matter as long as it's sorted. If it's not sorted, no chance. All right, let's just return true or false whether or not it's there. Okay, finding the location, not much different. All right, so here's what I'll do. I'll write a little function. I'll call it binary search, and I promise it's not difficult. Here's the data as the first parameter and the thing that I'm searching for the next time. Okay, ready for this one? This is the way I like to write my binary searches. If you search this up online, you'll find lots of varieties of these, but this is always my favorite. Okay, it looks a little chaotic to begin with, but trust me, it's easier to explain what I'm doing and what each line does. That's dangerous, right? It's an infinite loop. We're not supposed to do that. But remember, if I just return none inside the loop, is an infinite loop anymore? And the answer is no. All right, so as long as I get a return somewhere, it's okay. So we're going to do a search through values looking for the position 18, which should say true. Okay, and then we'll have to try some other things. All right, so here we go. Obviously, this does not solve the problem. Okay, well, here's what I'm going to do. It's always the same approach. When we were dealing with the slides back here, okay, let me go back and, okay, this picture right here does it, okay? Where was the first thing? Okay, so suppose this is the location, and I'm about to see if I can find it. What did I do? I have to look between position number 9 and position number 11, okay? I'm gonna give those two names, two very simple names. The position 9 I'm going to call left, and position 11 I'm going to call right. And this is going to explain where I'm searching. Like, for example, if we pick up this one right here, the value of left is currently 4, the value of right is 7. And when I do an extra step like this, the value of left is 6, the value of right is 7. Okay, so it's the beginning and the end. If you want to use beginning and end, you can. I think most people would probably use the other. They would probably use this left and right. To begin with, I have to search the entire thing. The very first position I'm interested in is 0. The very last position, length of data, -1, because you don't want to go off the edge. Okay, there we go. So you do this before. All right, remember what I kept doing over and over again. I picked out the middle. How did I find the middle location? I took the start and the end. Oh, sorry, the left plus the right, and divide by 2. There you go. That's the location. That's where I want to check. Next thing I did was I said, okay, every time I kept asking, if the data at the position mid was equal to the key, what this means is that I found it. Okay, that's it. Okay, just if that's what I'm searching for, then I'm done. Okay, what did I do otherwise? Okay, what I would do otherwise is I might have to ask, now usually I get this one backwards too, so don't worry if you get it wrong the first time. I would start asking questions like this. If what I'm searching for is smaller than what I found, or sorry, it's the other way. If what I found was smaller than what I'm searching for, that's usually where I get my mix up, what part do we throw out? Okay, so quick little test case. All right, so suppose we were looking for the value 71, okay? 71. Obviously, we would probably pop into a number like this. Yeah. Okay, I don't know if that's the exact middle, it doesn't matter. But which side do I get rid of? Well, I get rid of the first half. In other words, I want to change left. And I want to ignore the midpoint as well because I already know it's not what I'm looking for. Yeah, there we go, done. The alternative case, right minus 1. Right, because it's either you're going to move the left or you're going to move the right.
Yeah.
And you're going to exclude that midpoint because you know what you're searching for isn't there. Whew. Okay, now this will actually go and it will find things. Here's what I'm going to do. Let's return mid because that's the location. That way I can do a quick little check. All right, we'll run it. Okay, I'm taking my chances. Is 71 in my list?
Yes.
Yes. What's its location? Sorry, you can't tell me minus 1. We better count it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's position number 9. Okay. Let's find out whether or not it finds it. Yeah, that's pretty cool. Let's search for something else that is there. Let's search for the value 3. That is located in position number 1. Okay, yeah, so this is working. Now, of course, comes the problem. What if I'm searching for something that isn't there? You see, it should be there, okay, or if it was there, it should be between 71 and 79. I'm not going to run this because I already know this is an infinite loop, right? Because there's no way out. The only way out is if I find what I'm searching for. Yeah. All right, so here's the trick that I need to do, and exactly where you put it. You can either put it at the beginning or the end of the loop. It doesn't really matter. But I have one extra little trick. And if I ever end up with left being bigger than right, basically the two ends have crossed, that means that there's nothing left. So what I'm going to do is I'm going to return none or minus 1 if you want to do it this way. Okay, and there you go. There's a none. Okay. So it's not terrible. Right? It's not terrible. I can easily justify it. If you check online, you will find where they don't use an infinite loop. It's fine. Everything is completely legit. I just find that this way is really nice to explain it because there's a reason for everything. We built it up one piece at a time, and it matches that diagram really, really well. Give me a second because I know that I need this back later. So I'm just going to paste it over here into my notepad because I will want to come back to it. Okay, here we go. So through this whole horrible thing, okay, yes, we found it. And of course, usually at this point, somebody will say, so why would we do this? The reason why we do it is because you can find things really, really quickly. Okay, that's it. And I know that in this course, we don't really spend a lot of time worrying about efficiency of things, but I think it's important that we start to think about what things might make things faster or so on. All right, so there you go. There's the binary search algorithm. It's basically what I just demonstrated. The only thing that's different is the official one, because some people really freak out over infinite loops. It says while the left is less than or equal to the right. Okay, well, I had the same thing. I just like it as an infinite loop with a break at the end, or in this case, a return. All right, so yeah, same idea as what I just did. Left starts at 0, right starts at length minus 1, and you basically make a decision. If you found what you're looking for, then you stop. Otherwise, you adjust the left or the right. Okay, nothing funny about that. This one I propose that I won't do just to save a little bit of time, okay, but I will talk about it, and that is, okay, obviously, you cannot use that binary search if the array is a random mess. Okay, it doesn't work. Things need to be in sorted order. Otherwise, you have no idea which side to throw things out. Okay, so it has to be sorted. So I thought, hey, why don't we include a function to tell me whether or not something is sorted? That way you've got the algorithm. If you want to determine whether or not something is sorted, what you have to do is you have to go through each pair of items all the way from the beginning to the end, and you have to ask the question, because you can only compare two numbers at a time, you want to know whether or not the first number is less than the other number. So I think the easiest thing to do, let's get back over to here, and I'm going to ask a pretty simple question. Is my list right here sorted? No, how do I know? Okay, well, because every number gets bigger, okay? Let me give you a slightly different way of doing it because you can compare two values. You see, what I would do is I would compare those two values and I'd say, is the first one bigger than is the first one less than the second? And the answer is yes. So then I would repeat the operation right here and say, is the first smaller than the second? Yes, it is. And is the first smaller than the second? And yes, you can compare two things. You repeat it all the way. Is the first smaller than the second? Yes. Is the first smaller than the second? Yes. And because I made it to the end with never saying no, it's sorted. Let's make it out of whack. Is that sorted? And the answer is no, it isn't. All right, so how can you tell? Well, again, you do the same thing. Are those two okay? Yes. Are these two okay? Yes. Are these two right here okay? Yes. 18 and 49, is that good? Yes. And 49 and 40? No, because whenever you're checking the two things, it's the smaller number's got to come first. At this point, you can stop. You don't even need to look at anything else. So therefore, if this is ever false, don't attempt to run a binary search because you're going to end up not finding what you're looking for. Unfortunately, I don't know if I'd be able to actually get this to work. I mean, we'll try it. I'll try asking for 40. I don't know whether or not it'll find it. It says it's not there. Because I believe what happens is it looks at this number right here and it says what I'm looking for is smaller, so I'll ignore all the stuff to the right and I'll only search in here. So yes, you need to have this sorted. Otherwise, your binary search just doesn't work. All right, so all that I've done here by isSorted function is I just went through all of the items and I compared. I used a for I in range because whenever you want to compare two values, one to the next, you want to use a for I in range length, not a for x. Because if you're talking about for x in values, you can only look at one value at a time. And that's no good because you have to iterate through and you have to compare the current position against the next position or the current against the previous, whichever way you want to look at it. Okay, so that's why I ended up using a range loop, an index loop, to look at these values. Whenever you need to compare one number to the next number, you need indexes to do it. Okay, if you don't need them, don't use the indexes, use the easier one. Okay, now let's generate a real life problem. Okay, because somebody was asking earlier, okay, and no, this is not meant to be a tricky question. The problem may have been, well, hang on, we've got this little thing called in. Why wouldn't we use it? Right? I mean, it's here. Why wouldn't we use it? Okay, well, let's have a real life problem where we can't use it. Okay, here's what I want to do. Okay, write a function. Find GPA by student. Oh, hey, there's one of these. And this is the question earlier. Could I please iterate through a list of dictionaries? So let's do it now. Okay, so this is where it's going to pop in. What do I need? Well, I would need a set of students and I would need a key. Well, the key is probably the student ID, so I'm going to call it student ID. All right, how do we do this? Okay, we're looking for a GPA, and we're searching given the student ID. Okay, you know what? Let's go through this. For X in student list, print X. So here's some reviews. Let's go and let's search for something. We'll print find GPA by student. We'll pass in students and we'll pass in the ID 603145667. Okay, does that student exist? Yeah, they do. And what is their GPA? 2.8. Okay, so that's what this should return. Right now, okay, it's not returning anything, so that's why it says none, but I am printing everything. All right, do I see the information I'm looking for? And the answer is yes, I do. Okay, and remember, this is always the approach that I go. All right, perfect. So all that I need to do is just iterate through each of the items. So if you want to find something or you want to iterate through a list of dictionaries, it's just a for loop. Okay, now, of course, I'm not just interested in calling it as X. Each one of these things, I would probably call it a student. Okay, I'll call it ST just because I'm running out of names. But there you go. There's all the STs. I do see the person I'm looking for, but I'm seeing too much. Okay, because I'm really only interested in one student, and that happens to be if ST, well, students always have an ID. If that's what I'm searching for, oh, I called it not key, but I called it student ID, then I'm going to print ST. Okay, there you go. There's the one student. Oh, but I'm not interested in the one student, not the entire record. I'm only interested in their GPA. So let's use the dictionary property GPA to pull this out, and there we go. Now we've got it. Oh, but I don't want to print it. I want to return it. Okay, so here we go. Return st. Oh, and what happens? What happens if I don't find a student? I need to return something. I need to return something. Okay, there's a bunch of different possibilities. You check the code. None worked really, really well. Okay, there you go. So there's the 2.8. So if we're looking for something in a list of dictionaries, which was the request at the beginning, what you can do is you can simply set up an easy for loop, and yeah, just for whatever in student list. In this case, st, s would have worked as well. And you're basically pulling out the individual items to see if it matches. Does that look familiar? That is exactly the same pattern that we did earlier. Okay, just to remind you, way back on this page right here, well, that's pretty close, not exactly. I used what appears to be an index. Yeah, it looks like an index. And there's even a mistake in here because I forgot to increase POS every time. Whoops. Okay, I'll fix the slides. Because obviously that's an incorrect thing. So here we go, plus plus, and there you go. That's what it always looked like. Okay, you just couldn't see it. All right, but that's basically what I just did. I iterated through each of the items, and it really is the same algorithm. It just happens to be that instead of it being a simple integer, it was something a little bit more complex. Okay, it's still the same algorithm. So that's why I say you need to know the algorithm, because the algorithm keeps popping up in cases where you can't use in. Oh, could we use in to find the student? Well, you could, but you wouldn't want to. Okay, here, I'll show you how you could use it. Okay, and we'll find out whether or not we can use an in. Okay, so this is what I'm just going to call the key. Okay, and I'm going to print is key in students. Students. Okay, so I'm going to ask the question, is the key in the students right now? Yeah, is 345 in the students? No, there's no 345. No, of course it's not there. It's a whole pile of dictionaries. I'm never going to find an integer. So what it means is if I'm going to have any chance for this to work, I have to pass in a dictionary. Okay, so let's try this. ID 60314567. There we go. There's a dictionary. And is that key in the list of students? No, it isn't. There is a dictionary with ID 60314667 and a name, Sadal Nami, and a GPA of 2.8. That exists in the list. Oh, which means that if I wanted to use the in, I'm going to have to keep on going. I'm going to have to say, okay, is name equal to Sadal Nami, and I have to spell it exactly right, and the GPA is equal to 2.8. Is that student in there? And the answer is yes. So if I know absolutely everything, I can find the GPA. Oh, okay. But that means that I know the GPA already in advance. Yeah. And if I know the GPA in advance, why would I ask for it? Okay. Yeah, so here's one of the problems with this. Those in operators work really well if you are looking to find out if a known value is in something, usually a simple list. It works perfectly fine. Unfortunately, it's not realistic. It's not things we do all the time. We do sometimes, but this is more realistic because these are the types of things that we end up doing. Okay, let's see what I've got coming next. Okay, hey, if we can use a linear search, can we use a binary search on a bunch of students? Well, of course we can, but maybe just not directly. First of all, I'm going to ask the question, is my list sorted? Well, this is kind of a tricky question because what does it mean to be sorted? And we'll talk about this. This is actually something we'll do next Sunday. Is it sorted according to student ID? No, unfortunately it isn't. We can fix it, and we're going to. Is it sorted alphabetically? No. Is it sorted by GPA? So therefore, we cannot use a binary search on this. But, a little bit of work. Here, let's see if we can make it work. If I move this one up to here, okay, and I take this one and put it up to here, and I take this one and I put it right here. No, not there, right there. Okay, is my list sorted according to ID now? Okay, 60301234, 60303. Yeah, everything's going up. So I think it is sorted according to ID, which means that I can apply binary search. Okay, because if something is sorted, but I can only binary search if I'm looking for an ID.
Yeah.
Yeah, if I'm looking for something different, it's not going to work.
Okay.
All right, so somewhere over here I've got a binary search. Okay, now we'll find out whether or not this is going to work. Yeah, we're doing well for time. Again, sorry, I know this will go pretty long this time. All right, what I want to do is I want to binary search, and okay, we're not for searching for this, but I'm going to print binary search the list of students, and I'm going to search for, and sorry, I have to use double quotes because these things are already here. Let's look for 6031456667. All right, that person is definitely there. If I run it right now, bang, it's going to blow up because I got all kinds of horrible problems in here. Oh, I've got extra problems in here because I'm missing a comma, because I moved the last item around. All right, and it's starting to complain saying, hey, you can't compare instances of dictionaries. Yeah, that's exactly it. Because you see, I'm trying to search, please go away. I'm trying to search for a string, but what I've got is not an array full of strings, but in a list full of strings, I've got a list full of dictionaries. Yeah, that's because we're gonna have to do a little bit more work for it. All right, you see, when I do this key, that's the student ID. You see, I can't just look at the data at mid. I'd have to look at the data at mid given the ID. Now to make that decision. When I'm checking to see if it's less than, I have to look just at the ID. There we go. Any other changes? And the answer is no. The rest of the algorithm is exactly the same. At this point, okay, I don't know why that burned so much time. Okay, now it's fine. Okay, just a little slow on the laptop, not really sure why. But there you go. And that happens to be in position number 3. And yeah, there you go. That's it. And if I search for something that just isn't there, it comes back with none. It's a binary search, but the data is just more complicated. Oh, so in other words, but notice that the algorithm is really not that much different. I needed to modify it, but it's still the same pattern. It just happened to be that I had to look at one particular part of the items. Okay, but yeah, this is the reason why we cover this, is because sometimes you have these really big pieces of data with like complicated information like students or test scores or whatever else, whatever library books and so on. Yeah, you can still apply these types of things. Now, here comes sort of an interesting problem is, okay, great, we've done this. What can we do with it? Okay. I'm going to introduce something that's incredibly weird because I see what comes next is even faster. Okay, well, okay, this will be kind of like the final thing. The good news is, okay, so good and bad news. The bad news is I'm not finished, but the good news is what I'm about to show is actually really cool. Okay, it's not directly part of the course, so you're getting cool stuff when you're never going to be evaluated on it. Okay. At least I hope it's cool. It's got some very interesting things. So I'm going to steal little bits and pieces of this because I want to try, and after going through this just before class, I said I could really use a little bit more. Okay, here's what I'm going to do. I'm going to start with apparently copying something else, sorry. Copy, paste. All right. So I'm going to make my first little check here, okay, and I'm going to enhance it. I'm going to do a couple of things that aren't here, and I will also do what happens to be here. All right, import random. Okay, I know everybody's seen it. I'm doubtful whether or not it's good to show random in this course or even in 1101, but that's fine. Everybody knows what it does. It generates random numbers. All right, and random.randint generates a random number in the range of 0 to, what does that make that? Let's see, how many zeros have we got here? If there was a 1 right here, okay, it looks like 1 billion. Okay, so yeah, it's just a whole lot of numbers. Second thing that I did was I built up a list called data and I stuffed 1 million random numbers inside it. Okay, yeah, it's a big list. Is it a legit list? Do we have lists with 1 million things? Oh yeah. Think about all the stuff that shows up in Google searches. Oh, and by the way, if you say, yeah, nobody uses Google anymore because everybody's using ChatGPT, guess what? ChatGPT talks about a lot of parameters and so on, and yeah, they have a big number of parameters as well. You need to be able to find things, so it is legit. All right, so what I'm doing is I'm creating this really huge list of random numbers. All right, next thing up is I then go into a loop and I keep asking whether or not the number 45 is there. Oh, sorry, minus 45. The reason why I ask for minus 45 is because I know it's not there. It's the worst possible case. Okay, because if I happen to have 1 million items in my list and I'm searching for something that isn't there, using an in operator, which I said goes through each item, I have to look at 1 million things. I repeat it 500 times. The reason why I repeat it 500 times is just to make the program a little bit slower, because otherwise it finishes really, really quick. Okay, because if things finish really quick, it's hard to measure how long it takes. All right, and the final thing, which would be something new for you guys, even though it's actually legit something we could include, I make a call to a package called time, and I ask what time is it? Okay, and it gives me a number. I ask for the time before I start searching, and then I ask for the time afterwards, and when I calculate the ending time and subtract the starting time, it tells me how many seconds something just took. So in other words, what I'm doing here is measuring how long does it take to search 500 times for something that isn't there in a list of 1 million elements. Okay, that's what I'm doing. All right, everybody's computer, by the way, will have a different result of this. Okay, so here we go. We let the thing run. It takes a little bit of time. Okay, hopefully it doesn't take too long. Okay, all right, so 5.5 seconds. Or 5.4 seconds. If you run it 10 times, you get different answers every time, but they'll be all kind of close to this number. Okay, let's start writing some code, all right, because this should be great fun. Let's write a linear search. Okay, very, very quickly. Data key. All right, for x in data, if x is equal to key, return true, otherwise return false. Okay, yeah, it's a linear search. Right? All right. Instead of calling in, let's say linear search data minus 45. It's the same thing, right? All right, so let's find out how fast mine was compared to theirs. All right, was it as fast?
3 seconds longer.
Yeah, it was a little bit slower. Okay, well, it's fine. But you know, it's not that far off. Okay, how come? Well, because it turns out that using a for something in item, it is actually a little slow. If I was to switch it to a for I in range length data, it would actually be a little bit quicker. But the big difference is this is my code running, and the previous one where I had it just equal to in, that was built in. And yeah, they can optimize this a lot better. Okay, good. Oh, what am I going to do next? I just showed you a linear search.
Binary.
Yeah, of course, you know I'm going to do binary search. That's why I copied it. All right, except the binary search has this one nasty little problem. So here, I can just trash that one. Okay, this works. I don't need to modify it, except what's the requirement to make sure that a binary search works? The data has to be sorted. Okay. The good news is that there's a function built into an array called .sort. We'll talk about sorting next class, about how this works. Next week, we'll talk about how this data.sort can be used for complex objects, very important. All right, so what I'm going to do is I'm going to add all of these random numbers again, and I'm going to sort it, and then instead of calling linear search, I'm going to call binary search. Now, I'm going to warn you about something. Sorting operations are kind of slow. Okay, so what's going to happen is I'm going to run the program, and you're not going to see anything for a few seconds because it's going to be trying to sort this. So I'm just going to say a starting search. Okay, and yeah, sorting is kind of slow, and we'll see why next time. Okay, so here we go. We run it. So okay, so it wasn't too bad for sorting, but take a look at the time. That's really fast compared to what I did the first time. Yeah. Is that better than the in operator? Oh yeah, that was way better than the in operator. And again, if I run it a whole pile of times, you might get slightly different values every time because it just depends on what the computer is doing. But it seems to be like 0.1 to 0.2. It's a small number. If we increase the value, or the number of times I iterate, I might be able to get a little bit more accuracy out of this, but that's really cool. Okay, now you can start to see the reason why binary searches exist. It isn't just kind of for fun, but this is legit stuff. To put this into a perspective, it's not exactly related to this, but it's really, really close. The head of department was trying to run some query to check to make sure that grade books were set up correctly in D2L. And we wrote the script. It was something that I put together. And at the end, it ended up taking 35 minutes. Okay, but basically it was doing the equivalent of linear searching. Okay, and then I said, oh, okay, I know what the problem is, and because he was trying to check everything, I was only ever checking one, so if it took 10 seconds, who cares? But because he was trying to check all of the courses in the entire department, we needed to be a little bit careful about this. And okay, I didn't use this technique, but I used a slightly different technique, which is kind of related to what I'm about to show, and we got it down to 30 seconds. And 35 minutes to 30 seconds, it's a really big difference. It means that you can run it multiple times without taking so much time. All right, got another cool one. Okay, so get ready for this one. Nope, not this much. Okay, and this will be the final thing. This is the one that's on the slides, then we're done. All right, so here we go. Let me go back to minus 45 in data. All right, if I run this, we're probably back to our 5 seconds or so. Okay, just make sure we've got this back. Well, that's burning even more time. Okay, 15 seconds. Sometimes this happens. Okay, run it one more time just to see what's happened. Maybe it looks like if we're searching for sorted data, it seems to take longer. There could be some truth to that. It's hard to say how things get implemented inside the system. 13 seconds. Let me just get rid of this sort for a second. I'm actually surprised it's making that much of a difference. Did I change some other value? Maybe the computer's just running. There we go. So we're back to our 5 seconds. Okay, good enough. I'd like to make a small change. Okay, and I promise this will be the final thing, but this one's really, really clever. Yeah, you make a set. Okay, so list versus a set. Difference between a list and a set is that obviously it throws out duplicates. Okay. Oh, so is there going to be less elements than a million? Yeah. Typically, there's around 999,500 different values that end up being generated. So it's not quite a million, but it's actually really close. It's not like 20 elements. Okay. This is what I found. Instead of an append, how do you add something to a set? Just like what I said. All right, and I'm going to repeat this over and over again. Let's take a look at this one because this one's really quite surprising. Yeah, you see, that was super, super quick. In fact, most of the time when I run this, it actually comes back with the number 0. Okay, there it is. What it is, it's so fast that my simple little time can't actually measure it because it just ends up being like the same timestamp one after the other. But as I say, sometimes you end up with a number that isn't quite 0. Yeah.
Like just now, the dot sort it added 8 seconds to the...
Yeah, I don't understand why. We'd probably have to understand what's going on with the implementation of the list. Okay, I mean, it wouldn't surprise me if it was a different time, but I'm surprised by how much time it added. I have no idea. Okay, but sorting is slow, and apparently it also slows down the in operator on a list, which, as I say, is kind of unexpected. All right, so sorting works really well with binary searches. We saw this one, but this one's really clever because, well, I didn't have to sort it. Okay, and it's really, really quick. In fact, if I were to repeat this another, say, 100 times, just to try and get away from the 0, yeah, you can see this. Now, if I turn that back to a list and try this again, this would take, okay, it used to take 5 seconds, so now it would take 500 seconds. You want to try it? No, because class will be like more than finished by that time. All right, so we will save you the problem of doing this if you want to try it. The code is here in the slides. So all that I did was, again, okay, so this is, don't worry, the word hashing will never show up. In fact, I should probably get rid of it from the slides. But dictionaries and sets both use this really clever technique called hashing, which I'm just covering this in my other course right now. And the searches are super, super quick. It was really, really clever the way what they've done. And when you store something in a set or a dictionary, Python basically figures out exactly where it should go, and that's where it puts it. Okay, but this is way outside the scope of this course, so we don't talk about it. Really, all that I wanted to do is to say, hey, take a look at this. If you put something into a list and you do a linear search, it takes a certain amount of time. If you put it into a set, it goes blazingly fast. If you put it into a list and sort it, you can even apply the binary search really quick, and that, of course, is completely in scope. And I'm hoping that if nothing else that we get from this final slide is that, yeah, lists can be made really fast by sorting them and applying a binary search. Sets and dictionaries are blazingly fast, and you don't have to do anything extra. And if you wonder why do we have dictionaries and sets, this is quite often what I use it for, is if I'm constantly looking things up, and sometimes I end up doing this, then a set in a dictionary is a whole lot better than just a big long list, even though lists always feel like they might be just a little bit easier. All right. Usually at this point, okay, and then we'll be finished. Usually at this point, somebody will say, I don't understand what the questions might look like on the test. Well, a real-life linear search, well, that's certainly fair game. Right. I mean, that's the type of stuff we're doing in the assignment right now. And I think real-life binary searches are also kind of reasonable, so yeah, I would kind of recommend that you know this algorithm. Write it up a few times. Yeah, imagine the first few times I wrote it was also quite miserable. Yeah, just know the algorithm. You should be able to pull this together, like, I won't call it entirely by memory, but you should be able to justify and put one together fairly quick, because maybe at some point you'll be given a list of something that has been sorted and you're being asked to try and find it really quickly. Okay, and binary search, of course, is a really good option for doing this. All right, so do we go back and do we ask for like the time complex, or for, where did it go now? It's gone. Of course it was. It's easy to go back and it's hard to go forward. Do we have to worry about that little equation? No, but I think the ramifications, knowing that if you have a million items and you have to look at a million things, I think that's legit. All right, and let's see, this will be faster to skip back and forth so I don't have to look at my animations. So that's certainly reasonable. The overall algorithm, yeah, you have to know. Luckily, it's pretty decent. Sometimes we've asked like MCQ questions about this, and it isn't the type of, what's the output of this program? Sometimes it's like, okay, you have a linear search, you have a binary search, which one's going to be faster in this particular case? Okay, I've seen questions like that before. That's legit. We don't ask you to figure out how long something is going to take, but knowing the algorithm, I think that's legit. Knowing whether or not a list is sorted so you could apply something, I guess that's okay. And real life searching, yeah, I think that's all legit. And don't worry, there's never going to be a question about are sets faster for finding things in dictionaries or faster than lists, because the answer is yes, but this is outside the scope of this course. So the last one is just, as I say, kind of interesting, and no questions about it. Okay? All right. That's it for today. Next class, what we need to do is, now that we know if we sort something, it can be really fast with a list, so now we have to learn how do you sort things. And that'll be the next exercise. Okay, sorry for being a little lengthy today.